Timing synchronization.
So can you talk a little bit loudly? Shata.
Timing synchronization, sir.
Akshata, I'm not able to hear you. Is it possible to talk? Yes, what about Gautam? Gautam?
Yes, sir.
Yes, is it possible to just brief what we have discussed yesterday?
The timing synchronization.
Okay. Time synchronization.
Yes, sir.
What when I discussed about time synchronization yesterday? Hmm?
Yes, sir.
Hello?
Not able.
Huh?
It was time synchronization.
Time synchronization I discussed yesterday. Are you there yesterday for my class?
Yes,
You're there, man.
yes, sir. I was there.
Hmm?
Yes, sir. I was present.
You're present. But then I'm not getting the right answer, no? If you are there for my class, you should be able to tell what I discussed today. Time synchronization is day before yesterday's class. It is just I briefed in 2-3 minutes. Yes, sir. What about others? Swas Reddy, can you just say what I discussed yesterday?
Sir, 1 minute, sir.
Uh, yes, you require so much of time to just recall and say what I've discussed yesterday.
Sir, just sir,
Yeah. Yes, what about others? Other students? What about Vishnu?
So peak to average ratio.
Yeah, I discussed about peak to average ratio, right?
Yes, sir.
So is it possible to say what is the peak to average ratio for single carrier system and how the peak to average ratio is large for OFDM we say based on what? Yes, quickly. Others should yes, at least Akshata could say the name of the topic what I thought. Peak to average ratio. What about others? Whoever is there should respond, na? Yes, quickly. Yes, what about Teja? Can you say what I said about the calculation of peak to average ratio for single carrier system, and then the peak to average ratio for this OFDM? Why? Yes, Teja.
Sir, can I tell the definition, sir?
Yeah, you can tell the definition or even you can tell the value. See, I shown the proof, right? Clearly by
Yes, sir.
taking BPSK modulation. So what is the value of PAR for single carrier system? And I said, how do I say the peak to average ratio for OFDM is large? By calculating the peak power and the average power of the signal. Even after spending so much of time, if you are not able to grasp what is the key concept, I don't think it will yield any fruit. Then what you all do, just for sake of simplicity, login. I said now you have to be active, interactive. Hmm?
It is the ratio of maximum power of sample in OFDM transmit signal to average power of the OFDM symbol. That is called peak to average ratio.
Hmm.
Then average power of transmission is equal to A square by N.
Hmm.
And peak to average power ratio is equal to A square by N. That is equal to N. That
Hmm.
is, peak to average power ratio is equal to number of subcarriers in OFDM signal.
Okay.
If we perform IFFT operation, it leads to higher peak to average uh, peak to peak to average power ratio.
Fine, Teja. See,
Because of
okay, fine. Thank you, Teja. So what I said, the peak to average ratio for single carrier system will be equal to 1, I said, right? I said the peak power of the signal will be A square and the average power is also A square. With respect to that, I say peak to average ratio is 1. So which is nothing but, it is nothing but 0 dB, right? And then, so there is no issue uh, in case of single carrier system as far as the value of PR is concerned. But in case of OFDM, I said that PAR is directly proportional to the number of subcarriers used, right? So if I use more number of subcarriers, then the peak to average ratio will be high. So because of that, what happens when the peak to average ratio is large? Uh, there will be inter-carrier interference, I said, right? Because the power amplifier will be operated in the non-linear region. Okay, so actually to get the faithful amplification, we need to operate the amplifier in the linear region, right? But the practical characteristics of the amplifier, what it says is, so as the input voltage increases beyond certain voltage, it gets saturated. Output voltage is going to get saturated, right? So here, when the number of subcarriers are large, what happens? We are going to drive the amplifier into the saturation region. So with respect to that, there will be clipping of the signal, and I said there will be inter-carrier uh, interference, right? Means what we say is there will be a spectral regrowth, and as well as there will be tilt in the constellation. Okay, so these are the problems which arises due to high PAR in the OFDM. And I said these issues are okay for the deployment of this OFDM in case of base stations, because the base stations are less in number, right? And it will be, means as far as the LTE's approach to PAR in the uh, uplink, to say what are the things we are going to understand is, in case of I said it will be not an issue with the PAR for implementing OFDM in case of base stations, because I said number of base stations will be less, and the cost can be managed, because base stations will be there few numbers, right? But to incorporate this OFDM with high PAR in the mobile device will not be a correct one, because the cost of the power amplifier will become more and cost of the device will become more, right? And even so, to overcome that, there is an alternate approach to OFDM, and which is not that popular, but conceptually it is similar. Okay, so that is known as the single carrier frequency domain equalization. So the multi-user version of this single carrier frequency domain equalization is known as the SC-FDMA, so which is used in the uplink for LTE. Okay, so two types of multiple access techniques are used in LTE. From base stations to mobile station, OFDMA is the multiple access technique used. From mobile station to base station, the type of multiple access technique used is SC-FDMA, that is single carrier frequency division multiple access. So this SC-FDMA is what is the multi-user version of single carrier frequency domain equalization. Okay, so what I wanted to say here is this SC-FDE, that is the single carrier frequency domain equalization, is an alternative approach to OFDM for suppressing the inter-symbol interference. Okay, so this will keep the one minute. Yes, able to see the screen? Hello?
Yes, sir.
But I am not able to move the slides. Don't know. Somebody has changed some settings. Yes, yes, is my slide is changed?
No, sir.
Slide is not changed.
Yes, sir. Change, sir, now.
Change it. Okay. Thank you. Yeah, able to see the full screen, na?
No, sir.
You're not able to see the full PPT
No, sir.
slideshow? Slideshow you're able to see, right?
No, sir. We are not able to see the slideshows.
It is still a single. No. Yes, what about now? Now the slide has changed?
No, sir.
No. Are you able to see now? Hello?
No, sir.
No. Okay. Miss, now you are able to see the second slide?
Yes, sir.
Okay. Okay, fine. I don't know what is the issue. Fine. As I said, this single carrier frequency domain equalization is an alternative approach to OFDM for intersymbol interference suppression. Okay. With low complexity means it will be retaining some of the important benefits of OFDM. Okay. So it is maintaining or retaining three important benefits of OFDM. That is, one is low complexity. Even if the multipath is severe, in such case also it can provide a low complexity. Second one is excellent bit error rate performance, what we say. And third one is decoupling of the intersymbol interference from other types of interference. Okay. That is decoupling of intersymbol interference from other types of interference. What is that other type of interference? That is a spatial interference. Okay. So especially this is very useful when using the multiple antenna transmissions. Okay. So by utilizing single carrier transmission, it is possible to have less peak to average ratio. Okay, the peak to average ratio has been reduced significantly by several dBs, okay, with respect to multi-carrier modulation. Means when we compare it to OFDM, in case of SC-FDE, the peak to average ratio will be of around 4 to 5 dB. Okay, but as I said, in case of OFDM, when the number of subcarriers are around 512, I said the peak to average ratio will be of around 10 dB, right? But here with the single carrier, the peak to average ratio will be of around 4 to 5 dB. Okay, so let me try to understand, make you understand the block diagram of this single carrier frequency domain equalization. So here the first one is the OFDM transmitter and receiver. So, yes, I made it a slideshow possible to see.
No, sir.
No, it is no slideshow. Somebody has changed. Okay. Okay, I think with respect to this, now you are able to. Is it visible, my PPT? Are you able to
Yes, sir,
read?
it's visible.
Yeah.
Yes, sir.
Okay. Yeah, just I will tell in what way this SC-FDE is different from OFDM. Okay. So we know the first one is the OFDM transmitter and receiver. So what we do in OFDM, so this is my symbol, right? X is the vector information symbols. I pass that through IFFT, right? Then I get the time domain signal. Here it is a small x we denote it, right? Then we add the cyclic prefix. Then it will be a channel. Here there will be circular convolution is happening. Then at the receiver side, first we do the we are going to remove the cyclic prefix. Then we do serial to parallel conversion, take FFT, and then we do the frequency domain equalization, right? So I said, what is the purpose of this frequency domain equalization? The purpose of frequency domain equalization is to correct the phase errors and as well as equalize the amplitude variations. Then we will be able to estimate what are the transmitted symbols, right? So by doing IFFT operation in the transmitter side, right, I said the PAR, that is peak to average ratio, will be more in case of OFDM, I said, right? So how it is eliminated in the case of SC-FDE, that is what we need to understand. So what is done in SC-FDE is in the transmitter we don't do the IFFT operation. Okay, so I think we will be able to understand that. We're looking at, so the second block diagram is the SC, that is single carrier frequency domain equalization transmitter and receiver. So what is there in transmitter? So this X means this is the information symbols, right? So which are QAM modulated, right? So these are QAM modulated symbols. For that, the cyclic prefix will be added and then transmitted over the channel. So there will be circular convolution. Then at the receiver, what we do, we remove the cyclic prefix, do serial to parallel conversion. So usually we do the FFT, right? Then after this frequency domain equalization, here we are performing the IFFT operation. So what is happening here in the receiver, we are doing IFFT operation. So first we do the FFT and then do the IFFT. So this, by doing so, we will be able to cancel out that process. Okay, what is that? Increase in the peak to average ratio. So that is what the difference is. Then there will be estimation of the symbol. Okay. So in case of OFDM, we perform IFFT in the transmitter. Okay. In case of SC-FDE, that is a single carrier frequency domain equalization, we don't perform IFFT operation in the transmitter. Without performing IFFT operation on the input QAM symbols, directly we transmit by adding the cyclic prefix. Then at the receiver side, we do FFT and as well as IFFT operation. So by doing so, we will be able to able to reduce the peak to average ratio. I think I said by an amount of 4 to 5 dB. Okay, even for unmodulated sine wave can have a peak to average ratio of around 3 dB. So with SC-FDE, I said the PAR has been reduced to 4 to 5 dB. So with that, I can say it will be possible to operate the amplifier, power amplifier, and as well as the resolution of the DAC in a linear region. So without widening the dynamic range of the power amplifier. Okay. So, and this is what the expression, what I can say, FFT of the symbol Y of N, we represent as Y of M, right? So, which is equal to H of M into X of M plus noise. So, this is the estimation of the symbol, that is Y of M by H of M, what we say. Fine. So, in brief, I think you should be able to understand in what way SC-FDE is different from OFDM. Hope got my point. The thing is IFFT operation. Okay, IFFT operation will not be done at the transmitter of SC-FDE. The IFFT will be done at the receiver. So that will be the last process. So okay, so without doing IFFT operation at the transmitter, we transmit the QAM symbols by adding cyclic prefix. Then at the receiver side, first we do FFT and then do the IFFT. So with that, we will be able to means we are going to reduce the number of subcarriers. That's all. So, okay, so by doing so, we will be able to reduce the peak to average ratio. Fine. So the next one is the multiple access techniques. Okay, so hope you are aware of what are the different types of multiple access techniques. Okay, maybe in other subjects is might have discussed and studied also. So just it is I will give you the overview because we need to have the understanding of these things to understand further lectures of this LTE. Okay, so we all know the multiple access strategies are used to attempt to provide the orthogonal, that is non-interfering communication channels for each active base station subscriber link. Okay, that is from base station to subscriber, right? So the purpose of this multiple access is what? To provide orthogonal. Means if the signal is orthogonal, then what we can say is there will be no interference. Okay, that is what we say non-interfering communication channels for each active base station subscriber link. So while providing that non-interfering communication channel, right? So there are different ways to divide the available dimension among the multiple users. Okay, that is what it may be through frequency, time, or code division. So these are the three broad categories of dividing the available dimensions, what we can say. Okay, so one is if I divide the available dimension in terms of frequency, that I call it as a frequency division multiple access, right? So what happens in a frequency division multiple access is each user receives the unique carrier frequency, right, and bandwidth. Each user receives a unique carrier frequency and bandwidth. And I said each of those carrier frequency will be orthogonal. With that, because the frequencies are orthogonal and there will be no interference between other users in the same cell. Okay. Similarly, if I divide the available dimension in time, then I call it as time division multiple access, that is TDMA. So what happens in TDMA? Each user is given the unique time slot. Okay. You can use that time slot either on demand or in the fixed rotation. Okay, means you will be able to use the entire frequency, but over a small amount of time. Okay. Hope you're understanding what I'm saying. That is what the time division multiple access is. In case of FDMA, I said each user will be given the unique carrier frequency and bandwidth. But in case of TDMA, each user will be given the unique time slot. That unique time slot may be given either on demand or on the fixed rotation. Fine. So that is what is in TDMA. And then CDMA is what, that is code division multiple access. Here what happens? The user can share the bandwidth and as well as time slots with many users, but they rely on orthogonal. Means whatever the codes each user will be using, no, they are orthogonal, right? Or nearly orthogonal, what we say. They are the binary codes to separate out the users. This is as already studied, right? CDMA, that is spread spectrum communication. You know how multiple users can communicate over the same frequency and same time with their unique code, right? So that is what the CDMA system is. Means here many users will be able to share the available time and frequency dimensions, and each user will be differentiated by their unique code. Okay. So this is what the FDMA, TDMA, and CDMA is, right? Just what I can say is all these three multiple access techniques like TDMA, FDMA, and orthogonal CDMA will have the same theoretical capacity in an additive noise channel. Okay, what I mean to say is means they all can be designed to have the same number of orthogonal dimensions in the given bandwidth and amount of time. Okay, just to make you understand, I've taken one example. How do we say that in case of FDMA, TDMA, and CDMA, we can have the same capacity, right? So let us assume that it takes 1 unit of bandwidth to send the user signal. Okay, 1 unit of bandwidth, and there are 8 units of bandwidth are available. Okay, so each user requires 1 unit of bandwidth to transmit a signal, and I'm assuming that there are 8 units of bandwidth are available. Okay, so with this assumption, what I can say, 8 users can be accommodated with each technique, isn't it? Because 8 units of bandwidth are available, right? So 8 units of bandwidth are available. Each user takes 1 unit of bandwidth to send a signal, right? With that, each of those techniques like TDMA or FDMA or orthogonal CDMA can accommodate 8 users, right? So what happens in FDMA? How do I say that? How FDMA can accommodate 8 users? So there will be 8 orthogonal frequency slots, right? So we will be able to, because 8 bandwidths are available, I said, right? 8 units of bandwidths are available, right? And I said each user takes 1 unit of bandwidth. So in case of FDMA, 8 orthogonal frequency slots will be created, and one frequency slot will be given for each user. Okay, with that I can say 8 users can communicate, right? So in case of TDMA, what happens? Each user will be using all the 8 frequency slots. Okay, each user will be using the all 8 frequency slots, but at what time? He can transmit 1/8 of the time, right? Because 8 users need to use, it will be accommodating 8 users, right? So here time is divided into 8 slots, right? So let us assume that 8 microseconds. Each user can talk a period of 1 microsecond, but he will be able to use the entire frequency band. Whatever the 8 frequency bands are available, no? All those 8 bands units can be used by each user only for a fraction of time. Right. In case of TDMA, I said each user would transmit all of the time, right, over all the frequencies. Each user would transmit all of the time over all of the frequencies, but they can use only 1/8 of the available orthogonal codes. Means there will be here 8 orthogonal codes, only one orthogonal code can be used out of 8. Right? Why they should use only one? Means they will be able to use only one of the 8 available orthogonal codes. With that, they can assure that there will be no interference with the other 7 users. Okay, so hope we're able to understand with this example what each of those multiple access techniques are: FDMA, TDMA, and CDMA. Yes, I want response from your side. I took one simple example. I said each user requires 1 unit of bandwidth to transmit this signal. Okay, and assuming that there are 8 units of bandwidth are available. So how are we going to accommodate in case of each of the multiple access technique? I said 8 users can be accommodated with each of these techniques: TDMA, FDMA, and CDMA. Right? How it is done? I said. Hope this point is clear.
Yes, sir.
Yeah, I said in case of FDMA, 8 orthogonal frequency slots will be created. Okay, and one frequency slot will be allotted for each user. In case of TDMA, what I said, each user will be able to use all the 8 frequency slots, but he can transmit only 1/8 of the time. In case of CDMA, each user will be able to transmit his data all of the time over all of the frequencies, but he can use only one of the 8 available codes. Okay, one of the 8 available orthogonal codes. That is what? That is to assure that there will be no interference with the other 7 users. So this is what, in brief, I told about these 3 multiple access techniques. And with respect to this, I think you might have studied random access techniques. Is it possible to say what are the different random access techniques which you have studied? Yes, I expect you to answer this. Random access techniques. So this is multiple access techniques, right? Whatever I discussed so far. Are you aware of random access techniques?
No, sir.
Hello, my dear students. I'm asking, are you aware of random access techniques?
No, sir.
Random access techniques, what? Pranav. Then what you have studied in CCN, man? You have not studied about pure
So like
aloha,
Mac. No, sir.
slotted
Sir, like
aloha,
would be.
then CSMA. Are you aware? CSMA, that
Yes,
is
sir.
carrier sense multiple access.
Yes, sir.
Studied or not?
Yes. sir.
Yes, sir.
Yeah, they are the random access techniques. Okay. Okay, just let me have a brief review of that. So, I hope you are able to see this slide,
Yes, sir.
random access versus multiple access.
Yes,
Yes,
sir.
sir.
Yes, sir.
Yeah. Yeah, what I wanted to say here is in case of random access, right? So the users will be, means it actually uses the carrier sensing technique, right? So here the users will contend for the channel. Okay. In case of random access, users contend for the channel. So rather than being allocated a reserved time, frequency, or code resource. So in case of multiple access technique, this resource, what is that resource is? It may be time, frequency, or code, right? That will be reserved. Okay, that will be reserved in case of multiple access technique. But in case of random access, those resources are not reserved. So, okay, whenever the user wants to communicate, he will be contesting for that. So that is why it is called users content for the channel. Hope you able to understand the difference between random access and multiple access. In case of multiple access, the resources are reserved. What are those resources? It is time, frequency, and code. But in case of random access, the users will be contending for the channel. Okay, so we broadly classify these random access techniques are aloha, slotted aloha, then carrier sense multiple access. Okay, so what happens in aloha? So in aloha, that is pure aloha network, what we say, right? So that is a basic one. So what happens in case of aloha? Users will be simply transmitting his packets, okay, at his will. He will not bother about other users. Okay, users will be simply transmitting their packets at their will without regarding to other users, right? Then what they do means if the packet is not acknowledged by the receiver after some period, they will assume that the packet is lost and it will be retransmitted. Okay, so by doing so, what happens? That scheme will not be an efficient scheme, right? Because he has to wait for a certain amount of time, and he will be just assuming that when the acknowledgement is not received, he will assume that the packet is lost and he will be retransmitting, right? So if the traffic intensity increases, what happens? That leads to inefficiency, right? And as well as delay also, right? So that is what the drawback of the aloha. So to improve upon that, the slotted aloha has come into the picture. So what happened in slotted aloha? The users will be transmitting on specified time. Okay, so with that, uh, there is a certain amount of collision will be reduced in case of slotted aloha. Okay, so to improve upon, still there is not much efficiency improved when compared to aloha, but it is better than aloha. It is better than pure aloha in case of slotted aloha. Okay, so to improve upon the performance of this pure aloha and slotted aloha, the carrier sense multiple access technique has come into the picture. So here, in case of carrier sense multiple access, that is CSMA, what we say, we do the carrier sensing. Okay, what do you mean by that is here the users will be listening to the channel. Okay, first means before transmitting the data, right? The users will listen to the channel, and if the channel is free, then only they will be transmitting. Okay, that is what happens in carrier sense multiple access, right? Hope I convert what I said. In case of CSMA, that is carrier sense multiple access, the carrier is sensed. This carrier sensing is happening. That is, users listens to the channel before transmitting his data. Okay, why he will listen to the channel? To avoid the collisions whenever possible. Right, but in case of Aloha, what happens? User simply transmits his packet at his will without bothering about other users, right? But here, first he will listen to the channel, means he will sense the channel. If the channel is free, then only he will transmit the data. So there are variety of protocols have been developed for the CSMA protocol. In that, one of the most widely used is this one, distributed coordination function, what we call as a DCF. Okay, distributed coordination function, so which is used in 8.2.11. So here what happens in this protocol, so users will be waiting for the random amount of time after the channel is clear. Okay, so before transmitting his packets, why they will wait some random amount of time before they transmit their packet, to reduce the probability of two stations transmitting immediately of the channel becomes available, right? So if two users want are going to transmit immediately once they feel that the channel is available, then there is a possibility of collision, right? So to avoid that, they wait some random amount of time. Okay, so actually this CSMA is most popular and widely used in packet-based communication system. Okay, like Ethernet and even in wireless local area networks. Okay, so wireless local area network is nothing but what we can say, it is 802.11. Fine. Yes, is this clear? And even do you feel that the carrier sense multiple access technique, that is CSMA, has improved the performance to 100%, or even maybe above 90%? Is it possible to say what is the percentage of efficiency improved with the CSMA? Anybody is having any idea with respect to Aloha, slotted Aloha, and CSMA? Is it possible to say? Yes, quickly I'm asking. Hello. What is the efficiency Aloha? Yes, my dear students, see, all these things are known, studied, right? In computer communication networks, we have studied very much about all these things, right?
Sir, for Aloha, it's around 19 to 20%.
Yeah, Aloha 19 to 20%. Started Aloha,
It's almost double, sir.
it is almost double. Okay. Then in case of CSMA, theoretical efficiency of CSMA. Yes, what about other students? Vishnu was told about Aloha and slotted Aloha. Why others can respond, no? Even you're having mobile with you, you can just type and get the answer from your Google and you can answer. Need not remember. That is what the technology is now. Right? But even then you are not interacting. Hmm? You all feel that it is all irrelevant. See how much helpful if you have studied very well in the lower semesters, if you have understood those topics, concepts thoroughly, very easy to correlate those concepts to the upcoming technologies, right? See, whatever you study in the previous semester, you should not forget that. Yes, even then I'm not getting any answer. The theoretical efficiency of CSMA is carrier sense multiple access. Yes, respond others. Only Pranam is responding, Shreyas and then Vishnu. That's all. Hardly 3-4 students. Rest all what they are doing, whether they are listening my talk, lecture or not, I don't know. When you don't respond, when you don't answer, what can I understand? Yes, Chaitra, are you able to say what is the theoretical efficiency of CSMA? Chaitra? No, Chaitra. What about Anup? Yes, Anup. ನೋಡಿ ಯಾರು ಮಾತಾಡಲ್ಲ ಅಂದ್ರೆ ಏನು, ವೆದರ್ ಯು ಆರ್ ಇನ್ ಲೈನ್ ಆರ್ ನಾಟ್. ಅಕ್ಷತಾ ಮಾತಾಡ್ತಾಳೆ, she responds. Very few people. I am asking other people, they are not able to unmute and say yes or no. Yes, what about Sonali?
For up to 90%.
90% CSMA. ಇಲ್ಲಿ ಗೂಗಲಲ್ಲಿ ಸಿಗ್ತಾ 90% ಅಂತ? ಚೈತ್ರ
No, sir.
ಸುಮ್ಮನೆ ಹೇಳ್ತಾ ಇದ್ದೀರಾ ನಂಬರ್ ಒಂದು. Okay, the theoretical efficiency of this carrier sense multiple access is around 60 to 70%. Okay, and as I said, this carrier sense multiple access technique is being used in packet-based communication system, right, like Ethernet and wireless LANs. So in wireless LANs, the efficiency is observed to be less than 50%. Okay, even when there is only single carrier or single user, what I can say. Fine. Fine. So with this, it is just a brief introduction about these, just what I can say, a revision of multiple access and as well as random access, just to understand. Okay. So next one is, let me say about how these multiple access techniques like FDMA, TDMA, CDMA have been used with OFDM, right? Because I said OFDM is one of the technique which is, OFDM is not a multiple access technique, right? Yes or no? OFDM is used to mitigate the intersymbol interference, or what I can say, it is used to mitigate the frequency selective fading, OFDM, right? But by combining the frequency division multiple access with OFDM, okay, so that is known as OFDMA. Okay, OFDM, FDMA is known as orthogonal frequency division multiple access technique. Hope am I able to say? Yes, are you able to understand what I am saying? So now let us understand how these of multiple access techniques, like what I said about FDMA, TDMA, and CDMA, no, and as well as even random access. Anyhow, we are not going to discuss about how these random access techniques have been used in LTE, because that is not used. Okay, though it is. That is why I am concentrating on only how these FDMA, TDMA, and CDMA are used along with OFDM. And how do we say it is, what is that OFDMA, and what is the impact of these multiple access techniques, right? So to say that this, I said OFDM, FDMA, right, orthogonal frequency division multiplexing with frequency division multiple access, FDMA, is known as the OFDMA system. That is orthogonal frequency division multiple access technique. Okay, so the FDMA, what is that FDMA? That is frequency division multiple access, right? Can be implemented with the OFDM system. Okay, so by assigning different users their own sets of subcarriers. Are you able to visualize this? I said FDMA can be implemented in OFDM systems by assigning different users their own set of subcarriers. Means what? You assume the x-axis as frequency, okay, and it is usually we say with respect to 3D picture. Okay, x-axis is frequency, then time, then power, right? And we take a bank of subcarriers. All those subcarriers will be assigned to one user. Okay, that is what we get in OFDM, FDMA, what I wanted to say. Okay. Okay, so what I was saying is FDMA can be implemented in OFDM system by assigning different users their own set of subcarriers. So there are a number of ways to allocate. Means there are a number of ways this allocation can be performed, right? So means the one simplest method of doing is the static allocation of subcarriers to each users. Okay, that is the static allocation of subcarriers to each user. So just to understand, let me say that there are 64 subcarriers. Okay, there are 64 subcarriers in the OFDM system, and in that I am assigning user 1 to 16 subcarriers. Okay, hope you're able to visualize that. So without diagram, I wanted to convey. Let me see how many of you will be able to visualize that. I said I can combine, means I can implement FDMA with OFDM, I said, right? I can implement FDMA in OFDM system. That together is known as OFDMA, that is orthogonal frequency division multiple access. So how do we do that? I said the one simple way of assigning the subcarriers to each user is the what I said static allocation method. So to understand that process, I said let us assume that there are 64 subcarriers in the OFDM system. Okay, there are 64 subcarriers in the OFDM system. In that, user 1 will be assigned 1 to 16 subcarriers. 1 to 16 subcarriers will be assigned to user 1. Then for user 2, another 16 subcarriers, that is from 17 to 32. Okay, then the third user will be assigned from 33 to 48. Okay, and the fourth user will be assigned from 49 to 64. Okay, so totally I am going to assign these 64 subcarriers to 4 users. Okay, this is a simple static allocation. Okay, for each user I am dividing 16 subcarriers. Okay, so it is fixed. I said user 1 will be given 1 to 16 subcarriers. User 2 will be given 17 to 32. That is another 16 subcarriers. Then user 3 will be given from 33 to 48, and user 4 will be given from 49 to 64. Okay. So with this type of allocation, right? It forces, means the allocations are enforced with the multiplexer for the various users before the IFFT operation. So with that, even what I said here, 16 are equally allocated, right? With for 4 users, even it can be uneven allocation also. Okay, to achieve high data rates, right? That means I said depending upon his requirement, if you are able to supply a required number of subcarriers, then we will be able to achieve the high data rate, right? So that is known as the dynamic allocation. Okay, so instead of doing static allocation, if you are able to provide or achieve the dynamic allocation of these subcarriers, so you will be able to achieve the high data rate, right? So let us see how this dynamic allocation of subcarriers in case of OFDMA made the choice for use as a downlink multiple access technique in case of LTE. Okay. So I think with this brief idea about OFDMA, and that is the use of OFDMA and FDMA, I will stop today. So let me continue with other multiple access techniques like OFDM TDMA and OFDM CDMA. Then we will take up in detail about OFDMA. Okay. I think you people can